has been ported to new architectures that are still in simulation stage way before the silicon is even ready. So they got Linux boot up, in an emulator, that is just emulating the new architecture that will be released like a year later. Okay, so that really kind of gives you an idea of the ability of open source products, because anyone who needs to get it done, if they have the know-how and the time and the resources, they can get it done. Who would do something like this except for geeks who got nothing else to do?
People are manufacturing the hardware.
People who are manufacturing the hardware, and also researchers. Okay, researchers in major universities, they want to test new architectures, so they would design the architecture without the silicon. But in order to understand and benchmark the features of a new processor, they need to run something, right? They cannot just oh, okay, these are the new cool features, and we think it is going to be superior. This is a superior product. So they have to kind of really run it in a real environment. And Linux lends itself to this type of research because they can rewrite only a portion of the Linux kernel in assembly, for this new architecture, and then they can leave the rest, in C, and it's relatively easy to have Linux ported to a different architecture. They have to port GCC first, the compiler, but there are people specializing in that sort of thing as well. So if you give the description of the new architecture to people who specialize in the back end of GCC, they can finish the back end of the GCC and make it generate opcode for the new processor in a relatively small, a short time. Okay. I know people like that. That's what they do all day long, is to port GCC to different processors, different architectures. Okay, so getting back to this. However, this apparent disadvantage solves our second problem, which is something that I just illustrated, because you don't need that many bits to specify which register you want to use. So you make your instructions smaller, narrower, and it doesn't take as long to fetch your next instruction. At some point, the ALU needs to get data from memory or store result in memory. However, the use of registers greatly reduces the need of accessing memory. When you write your programs in C and C++, how many people use GCC on the command line and actually run, say GCC blah 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 to compile your program?
I would think so.
Okay, very good. Did you use Did you specify dash uppercase O to and so on and so forth? What does that do?
Optimizer.
The optimizer. All right. So what does that do? What does an optimizer do? How does it do it? How does it optimize? Can you name one trick that the optimizer can do that is related to registers?
Can store local variables in registers.
Exactly. So the optimizer will basically look at how you utilize your variables. If it finds that a particular variable is used frequently in a subroutine, then it will say, hey, since this thing is being used all the time, it doesn't make sense for me to write it into memory and then read it from memory again, write it into memory and read it from memory again. I'll just keep this one in one of the registers, because a register is so much faster than accessing memory. So this is one of the tricks that an optimizer can do, is to determine which variable in your code can benefit a lot from moving it from memory into registers. Okay, so as a result, the more registers you have in the processor, the better the optimizer can get its job done, because now instead of playing with only 4 general purpose registers, it has 8 or 16. So your program can potentially run a lot faster as a result. You had a question earlier. Go ahead.
Does the register keyword in C++ or C does the same thing? Does it do the same thing?
That's a good thing you bring that up. The keyword, or the reserved word register in C and C++ is a suggestion to the compiler. So it's telling the compiler, well, maybe we should put this one in a register. But whether the compiler actually puts it into a register is up to the compiler. So you cannot count on it. Okay? So most people don't use that register reserved word anymore, because it's not really that helpful. And most of the time, the optimizer can do a better job than you or most other programmers to determine, what is the best way to utilize the registers. How many people know of the reserved word volatile in C and C++?
I've heard of it.
And how to use it properly? Volatile is basically anti-optimizer, okay, if you see it in a certain way. Because sometimes, you might have you might have a variable, especially global variables, that is used to let an interrupt surface routine or signal handler to communicate with the rest of the program. In other words, the variable can be changed, quote unquote, in the background. Now, for those types of variables, you don't want it to be stored in the register. You always want to read from memory locations, because another thing like a ISR interrupt surface routine, which we will talk about in this class, or a signal handler, can be changing that variable, quote unquote, in the background without your own subroutine aware of the change. So for those variables, you always want to say, okay, don't put this one in the register because I want to read from memory every single time it is accessed. I want to write it back into memory every time I'm done updating it. And that's basically one use of the volatile keyword, is to make sure that those things are not optimized when it's not supposed to. All right, cool. Are there any questions with this page? Why registers is a solution, how it solves the problem that we had? No questions? Right. Looks like half the class need more sugar right now. And the other half needs more caffeine. I need both. All right, the impact on the instructions. Because of registers, instructions need to be able to specify memory locations and registers. Some architectures allow an instruction to specify a mixture of registers and memory. Instructions is in quotes in this case because this I am referring to mnemonics as opposed to opcode. A single mnemonic can have any number of opcodes corresponding to it. Okay, this is all about what you see when you're a programmer and how what it translates to in binary code. Okay. Architectures that permit mnemonics to choose between registers and memory are typically conventional CISP or complex instruction set computers. The Intel architecture definitely falls into this category. Other architectures, however, partitions instructions so that only certain instructions can access memory. This scheme enjoys the benefit of an extremely small number of opcodes. Most architectures that partition memory access instructions are RISC architectures. Okay, so let me just kind of briefly explain what this means. The i386 instruction set, at least from the perspective of mnemonics, okay, what you'll be using to write the programs, from that perspective, you can specify this one, using the same mnemonic like add. Okay, I'm just going to use one that is really generic. So when you use the add instruction, you can specify, these three things. I'll just say there are three things, but there are actually only two. But you can specify this one comes from memory, this one comes from a register, and this one goes back to a register. Okay, and then in the next add, in a different add instruction, you can say this is coming from memory, this one is coming from memory, this is storing to a register. So they all have the same word add to perform that operation. It has the same mnemonic. But you can use a mixture of memory location, register, register, memory location, register, or register, 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 and so on and so forth. In some other architectures, the add instruction can only deal with registers. So how do we get something into registers? We have a separate set of instructions to move data from memory into registers and from register back into memory. So your computation instructions can only work with registers, but you have specific instructions to move things from memory into registers and from registers back into memory. Okay, and that really separates what is RISC and what is CISC, because a CISC architecture can usually would let you mix up the registers and memory access in the same using the same mnemonic. RISC architectures, on the other hand, will typically restrict the computation instructions to only use registers and then give you a separate set of instructions to move things around. or copy things around, I should say. Are there any questions about this discussion? Yep.
So which one are we going to be using?
We are using the i386 architecture, so we'll be using the cisp architecture. You can choose, each part of the instruction. This is called an operand. So for each operand, you can choose, where it gets, that information. Yep.
What's an example of a RISC architecture?
The ARM architecture, commonly found on cell phones. The Atmel, AVR architecture, which is used in the Arduino projects. So those are all prime examples of RISC architectures, where the add subtract instructions can only work with registers, and in order to load something into registers or to save it from register to memory, you need a different instruction to do that.
PowerPC.
Sorry?
PowerPC.
PowerPC. PowerPC is a very interesting architecture. It was actually designed to make the emulation of another processor efficient. And it is still being used by IBM. Yep.
Power 5.
Yeah, IBM pulled a quick one on Apple, and told Apple, you know what, we're not going to make any power-saving PowerPCs. If you want power-saving processors, look elsewhere. And then Apple just couldn't deal with it and went to Intel and go, okay, we're switching to the Intel architecture. Right after that, IBM improved their PC architecture to make the low-power versions. Yeah, just to ditch Apple, they say, no, we're not going to have a low-power version of our processors. Because Apple is a pain in the butt. Because they keep requesting all these things, and IBM has no interest whatsoever to surface Apple in that context. Of course, the PowerPC is also used in one really famous, well, I guess it's one of the popular game consoles. Which one? Well, it's certainly not the Xbox. The PS3, PlayStation 3, or 2. PS3, I think it's the PlayStation 3.
It's 3 with the cell subsystem.
Yeah, the cell processor is actually PowerPC based. Yep.
Yeah.
And of course, when Sony says, well, you cannot install and use a third-party operating system, that really made a lot of people not so happy, including the Air Force of the United States. Does anyone know why?
They ordered it.
Why did they order a bunch of PS3s? Do they want to use it for flight simulation and stuff?
For Linux, I can't remember what they were doing.
They were using the cell architecture, to make
Missile guidance.
to make what?
Isn't it missile guidance?
They were turning into a cluster, into a superpower computer, into a powerful computer cluster. I don't know what they're using it for, but it's really, they're using it as an inexpensive way to make a computer cluster, so they have tons and tons of processing power without having to pay a lot of money. But they needed to run a third-party operating system to get it to work. So when Apple says, no, after this update, you cannot use a third-party operating system, how did the Air Force ended up doing after that?
They wanted a refund?
They want a refund. I don't know. They can probably go to the headquarters of Sony and protest.
I'm sure the Air Force is getting by fine without PlayStation 3s. I'm sure the Air Force is getting on fine without PlayStation 3s.
Yeah, they just took all the PlayStation 3s home, right?
Send them to the USOs.
Christmas gifts?
$1 billion.